Hi, this is Kani Patel. Today we are going to discuss about symbolic analysis of privacy for TLS 1.3 with encrypted client hello. So this work was presented by Karthikeyan Bhargavan, Vincent Sival and Christopher Wood. So first, what is the motivation? So as we know, TLS 1.3 is the newest version of Transport Layer Security Protocol TLS, which provides strong authentication and confidentiality. Despite its controversial use of handshake encryption, the privacy guarantees of 1.3 still remain a little weak and may be poorly understood. To close this gap, IETF TLS working group is standardizing the new privacy extension called Encrypted Client Hello. So, there are several drafts on TLS 1.3, and some of those drafts were found to be vulnerable to the active network attacks. So, this protocol requires some formal analysis, and these authors have tested TLS 1.3 using the symbolic protocol analyzer, which is ProVerif. So the first question is TLS 1.3. So why TLS 1.3? So as we know that in the TLS 1.2 handshake, we can reduce RTTs using the TLS 1.3. So in TLS 1.2 you can see before the data exchange there are two RTTs, whether in TLS 1.3 we can exchange the key and certificates in just one RTT. So TLS 1.3 is basically faster and more secure than TLS 1.2. So how TLS 1.3 is more secure? You must have remembered that in the assignment 2 where there was one exercise where we had HTTP request. So in the HTTP request we can change the header information, and yeah, that's the thing, we can change the header information because it was not encrypted. But here in the TLS 1.3 our packet will be encrypted, so it will be hard to change the header information in TLS 1.3. So let's see. So basically ECH denotes that it's an encrypted client hello, and before the client hello was encrypted, we know that server name indication. So in the header there is a server name indication. So we don't want to reveal our server information to the active attacker, right? So we encrypt that part. So here this is the client making a request and this is the backend server. So between the backend server and client there will be one client facing server. So what client will do, client will encrypt the server name indication so that this client facing server will decrypt it, and then it will send request to this backend server, so that if there is a attacker in the middle, so the attacker won't be able to read out that message. So encrypted client hello. To improve the privacy of TLS 1.3, IETF TLS working group is standardizing a new protocol extension called encrypted client hello. The key idea of ECH is to encrypt parts of client hello in order to hide the server name, pre-shared key and other handshake metadata. So here you can see that every server has some built-in mechanism, right? Some server might be old, so they won't support the TLS 1.3 with ECH, and some might support. So if clients send a request with ECH, there will be two parts in client hello packet. The one is inner client hello and another is outer client hello. So if server supports ECH, inner client hello is used in transcript and inner key share is used for Diffie-Hellman. You can see here that this is TLS 1.3 plus ECH. This server supports it. So when the key share will happen, this is the normal key g raised to x, and this is the new key g raised to xi. So if server supports ECH, then in the transcript, means in the response, server will send that it accept tx1, and in the calculation of tx1 it will use g raised to xi, which means that inner client hello is used in transcript and inner key share g raised to xi or x dash is used for Diffie-Hellman. Otherwise connection falls back to standard 1.3 and outer client hello and its key share will get used. So what should be our main goals while creating TLS 1.3 with ECH? So our goal should be that it should provide authentication and integrity. So what are the main parameters? So for the authentication and integrity, it should provide server authentication. What do we mean by server authentication? That if a client C receives application data message over TLS 1.3 connection with server S, then either there must be an honest server S that sent the message M, or else S must be compromised. What do we mean by client authentication? It's similar that if server S receives application data from client, then the client must be honest client, or the client C is compromised. Then key and transcript agreement. If a client completes a handshake with honest peer, then both parties must agree on connection keys. That means that KC, KS, that both client and server should agree on this key. Then we have data stream integrity. If a client receives a sequence of message over TLS 1.3 connection, then either an honest peer has sent the sequence or peer must be compromised. Next one is unique key, like key uniqueness. So two different TLS connection cannot result in the same encryption key. So if there are two different connection, then there must be two different keys. So similarly, downgrade resilience. By downgrade resilience, we mean that if a client completes a handshake with an honest peer and both parties prefer to use certain protocol parameter, then the handshake cannot end with less preferred parameter. So it's like if both the parties have TLS 1.3 plus ECH, then both will go with TLS 1.3 plus ECH, not with just TLS 1.3. What should be our goal while creating? So another goal is confidentiality. So what do we mean by confidentiality? That the message we transfer from client to server should be confidential. So first is key secrecy. So if a client completes a handshake with data encryption keys, then either the peer is honest and keys are unknown to the adversary, or the peer is compromised. So then next is key indistinguishability. So if a client completes a handshake with honest peer to obtain a new key, then this key is indistinguishably from fresh random value generated at the end of the handshake. The next one is 1 RTT data forwards accuracy. So, yeah, this is the important thing, that if a client send a secret 1 RTT data over TLS 1.3 connection, then M remains secret even if the peer is compromised. So, like, how is this possible? Because in the TLS 1.3, for the 1 RTT data connection, the client and server use ephemeral keys. So for each connection, client and server both will generate new keys. So KI1, this is KS1. So if there is a second request, then for each request, client and server both will generate new keys. So even if after the connection and one key is compromised, that doesn't mean that all of the data message will be known to adversary. And then another is 0 RTT data accuracy. So if clients send 0 RTT application data with TLS 1.3 connection, then this message remains secret unless pre-shared key is not compromised. So if the pre-shared key that is used in 0 RTT connection is not compromised, our data is safe. And if that key is compromised, then adversary can read the 0 RTT data. So then again, what should be our goal? So the third point is privacy. So like when we make a connection and share data, we want our client to be client identity to be private, right? So if one of the two clients A and B are connecting to the server S, then attacker should not be able to tell that which of the two clients made the connection. Then client unlinkability. So if A and B both make the connection with server S, then one of them makes a new TLS connection to same server S. So the attacker should not be able to tell that out of A and B which one made a new connection. Then server identity privacy, that if we are making a connection with server, suppose there are two server S1 and S2, and there is one connecting server F. So like if we are making a connection, then adversary should not be able to tell that whether we are making the connection with S1 or S2. So it should provide server identity privacy. Then the next thing is client and server extension privacy. So if client or server sends an extension with a sensitive payload over TLS 1.3, then the attacker cannot distinguish between different values of payload, right? So each privacy goal must hold even for a partial handshake. Even if the partial handshake fails, the privacy goal must hold. We shouldn't be revealing the client or server identities to an adversary. Like it is important for the successful connection, but even for the fail or half completed connection, it shouldn't reveal this information. Then TLS 1.3 with SNI. So it's a server name indication. So TLS 1.3 was fail to provide server identity privacy, because the thing is, even if we used encrypted SNI, but in the token, or when server sent a retry message, in those packets it was revealing the server information. So if we are making a connection, this is our client hello, and server is sending retry. Server is saying to send new client hello to the client, and if there is an attacker in the middle, so even if we are encrypting the SNI in the client hello packet, if server is sending the retry packet, there will be some information which will reveal the server identity to the attacker. So like, how can we prevent that? Even it does not provide client extension privacy. So what about client 1.3 with ECH? So what happens if we encrypt the client hello packet? So this author has used a tool and made some experimental evaluation for TLS 1.3 plus encrypted client hello packet. So author has tested TLS using proof. The full TLS 1.3, so in their setup they made a code of total 7600 line, and they set up there are some parameters, right? So resource limit for proof, they set up a time limit of 48 hours for the testing, 100 GB of memory, and these are the RAM and those parameters. So they have tested this protocol on the proof testing tool, and these are some of the results that they got. So you can see here some of the short forms. So let's discuss. So this is for TLS 1.3, this is for TLS 1.3 with encrypted client hello, same as here. Okay, so for the TLS 1.3, they had enabled all of this. They had enabled one RTT connection, then group negotiation was also on, client certificate, they send client certificate, everything was on, and average testing time was 10 hours. And with everything on, TLS 1.3 was successfully giving the result. So these all are true. So let's see, if we do not enable 0 RTT data for TLS 1.3, it will successfully provide SEC, means key secrecy and key uniqueness. So it makes sense, right? If 0 RTT is disabled and only one RTT is there, then there will for every connection the key will be unique, and it will also provide forward secrecy. Because in the 0 RTT connection, if pre-shared key will get revealed, then it will not provide any secrecy. Even the key won't be unique for the connection, because we will use the pre-resumed key for new connection. So with 0 RTT disabled, we get all those successfully. So similarly, we can see for the 0 RTT secrecy that in TLS 1.3 with ECH, if we do not send a client certificate, then we can achieve zero RTT accuracy. So let's see here that in TLS 1.3 with ECH, if we want to prove client identity privacy, so we want to make our client private and client unlinkability. So if we do not send back the ticket, then we can achieve the client identity privacy. So the thing was with TLS 1.3, there are certain parameters which we have to tune out to use certain property. Okay, so what were the observations? So ProVerif succeeded in verifying all the reachability property for TLS 1.3 without ECH. We can see here that without ECH, it verifies all of those properties. But with ECH, it ran out of memory in all the other cases. The author ran ProVerif on various combination of features for each property. There were total 621 total analysis runs, from which we selected best result combination to show in the table. So out of 621 total analysis runs, author showed us this many. ProVerif is able to prove key accuracy and key uniqueness with zero RTT disabled. So as we see here, with zero RTT disabled, it provides key accuracy and uniqueness. Just like that, accuracy of zero RTT data is then proved with client certificate disabled. Since certificates only appear after zero RTT data has already been sent, disabling it has no impact on this property. So if you go to Google and search ProVerif tool, you'll find this link and you can check this out. So what were the limitations of this testing? So symbolic models can't capture side channel or real world leaks, right? For example, even if we secure the SNI using the encrypted client hello, but what about DNS lookups? So DNS lookups will still reveal the domain name before TLS handshake begins. Similarly, traffic patterns, packet size, or timing information could leak which site is being accessed, even if the handshake itself is encrypted. So this is the IATF documentation for the TLS. You can even check this out. And for the future work, as we know, Quick is using the TLS 1.3. So extending this analysis to Quick, since Quick also embeds TLS 1.3, is important. Then analyze session resumption and pre-shared key use cases, which are more complex and might affect privacy guarantees. So we tested it with, it was working fine with one RTT, but what if there is a pre-shared key use cases? So for this testing also requires some work, so we can save it for the future work. Okay, so that was it. Thank you so much.